This is problem 2A4 out of our dynamics textbook. First thing I would like to point out is that this is a case 2 scenario. So that is something to keep in mind as we start to work through this problem. So the first thing that we're going to want to do is find an equation for our omega value. And we can do that by using the equation that we've got from the chapter 2A for velocity. And that equation is V of A equals V of B plus omega cross R of A slash B. And as you work through this, your omega equation will come out to the negative value of V of A minus V of B, all divided by big R plus little r. Part of the reason that this being a case 2 scenario is so important is because we can assume that the velocity from the A rack will move the inner wheel at the same speed at the top. And the same thing for the bottom, or the B rack. We can assume that the bottom of the outer wheel will move at the same speed as V of B. Just to check your work here, the value we got for the numerical solution is 5.385. The next step in this problem is to find an equation or a numeric solution to alpha. And we can get this by using the acceleration equation that we've been using so far in chapter 2A. And that equation is the acceleration at A is equal to the acceleration at B plus alpha cross R of A slash B minus omega squared times R of A slash B. As we work through this equation, it is important to break up the acceleration into each of its components, meaning in the I and the j direction. So for this equation, we'll end up with A of A in the I direction plus the acceleration of A in the j direction equals the acceleration at B in the I direction plus the acceleration at B in the j direction plus alpha cross R of A slash B minus omega squared times R of A slash B. Since we know all of the values that we need for this equation, we can solve for alpha using the I component of the entire scenario. And we can get that alpha is equal to the negative acceleration at A in the I direction divided by the quantity big R plus little r. And once again, just to check our work, the numerical solution that we got is that alpha is equal to negative 7.69 radians per second squared, and that would be in the k direction. That the majority of the initial setup is out of the way, we can actually start solving for the velocity at point P. And in doing so, we can use the equation that we've got from this chapter for velocity. That equation for this point in the problem would be the velocity at P equals the velocity at A plus omega cross the R of P slash A. So now that we have this equation started, we can start working through the cross product. And one thing I would like to point out that the value for R of P slash A is equal to big R in the I direction minus little r in the J direction. So after you work through this, you can get that V of P equals V of A in the I direction plus W times big R in the J direction plus W times R in the I direction. So at this point, what I'd like to do is I would like to group my I direction and J directions together. So we can get V of P equals V of A plus W times little r all in the I direction plus omega times big R in the J direction. So since you know all of these values, this would be the final equation for the velocity at point P, and you can go ahead and plug all of your values in for this and solve for the final velocity at point P. So now that we've solved for the velocity at point P, we can move on to finding the acceleration of point P on the outer rim. And we can do this by using the equation for acceleration that we've gotten from this chapter. That equation is A of P equals A of B plus alpha cross R of P slash B minus omega squared times R of P slash B. One thing I would like to point out that R of P slash B in this case is R in the I direction, big R in the I direction, plus big R in the J direction. So as you work through this cross product and start to simplify this equation a little bit piece by piece, you can get a of b y in the j direction plus alpha times r in the j direction minus alpha times r in the I direction minus omega squared times r in the I direction minus omega squared r in the j direction. One of the issues with this problem, however, is that you don't know the acceleration of b in the y direction. So one thing we can do is we can solve for that using the acceleration equation that we've used so far throughout this problem and in this chapter. And to set up that equation, we can get the acceleration at point O is equal to the acceleration at point B plus alpha cross r of O slash B minus omega squared times r of O slash B. And as you work through that, you can do the cross product and simplify all the terms, and you can get that the acceleration at B in the y direction is equal to omega squared times r. So now that you know all of the variables for this equation, you can go and group it into its I and j components. So you would get that negative alpha times r minus omega squared times r in the I direction plus alpha times r in the j direction would be equal to your acceleration at point P. And in doing so, you can go ahead and plug in all of your numerical values for this equation and solve for the numerical value for the acceleration at point P, and that would be the end of this problem. So what you're going to see here is the work finish up, and then that will be it for today. Thank you guys.